So let us start with signal transmission through linear systems. So the initially let us understand how do we represent a continuous system with the help of a differential equation. Consider the given system S to be a continuous time system where input is given as x of t and output is y of t. So firstly, let us understand the concept of linearity. So when you talk about linearity, we've already seen in the earlier classes that two different phenomena have to be met. The first one is homogeneity and the other one is additivity. Both of them together is called as the superposition. So according to linearity, we say that a times x1 of t plus b times x2 of t, where x1 of t and x2 of t are inputs to the same system S and a and b are constants, will give an output a times y1 of t plus b times y2 of t. If this happens, then we assume that we confirm that the system is linear in nature and it needn't necessarily be only two inputs and two outputs. It can span to multiple inputs and is 1 to infinity an xn of t. If this gives the output, m runs from 1 to infinity bm ym of t. Then we claim that the system is linear in nature, and we have seen a few examples of linear systems earlier where y of t is x of 2t. This is a linear system, and y of t is t times x of t. This is also a linear system, right? So the other aspect of it is time variance and time invariance. So when you talk about time variance, time invariance. What do you mean by time invariance? If the input has undergone a delay of t naught seconds and the same delay is reflected in the output, then you call that system time invariant. Else, you call that system time variant. So, two aspects that we require here is for a system to be represented in the form of a differential equation, especially a continuous time system, we need to confirm that the system is linear and time invariant in nature. Time invariant in nature, which is called as LTI, LTI system, right? So if this happens, then we can represent any given system in the form of a differential equation and analyze it. That is the basic importance of it. Now, why is LTI very important when you talk about any given system? Let us start with that and let us start by understanding a few terms first. The first term being impulse response. Impulse response. So what do you mean by impulse response? All of us understand the signal impulse, which is defined as del of t, and by definition del of t is equal to 0 when t not equal to 0. Right, by definition it is that, and then integral minus infinity to infinity del of t dt is equal to 1. This is our Dirac delta function that we have known all along. Now what do you mean by impulse response? If you give impulse as input to any system S, the response that you would be getting. Or in other words, if input to a system is impulse, the output that you would be getting is called as impulse response, which is defined as h of t. This is impulse response and the input is impulse. So why is h of t very important basically? So in general notion, what we say is if the impulse response of any given system is known, then the output response y of t for any arbitrary signal x of t can be known, provided the signal can be decomposed into elementary impulse signals. Let me repeat it again. Here, what are we saying? The input, if it can be decomposed into elementary impulse signals, elementary impulse signals, then output of any given system S, output of any given system can be known. So this is how it starts basically. Now what is the basic concept behind it? First, let us see how x of t can be decomposed into elementary signals. We will try to understand that by going into the discrete domain. That is much easier to understand. So when we say discrete domain, we are talking about x of n rather than x of t. Now first suppose I take an example of this given signal n, and all of us know that n only exists for integral values of time, unlike the continuous time systems which exist for discrete values of time. So let us try to represent this in the form of impulses. Right? Let us try to write x of n in the form of impulses. As all of us know how to express the given signal in the form of impulses, so the given signal can be written as 1 times del of n plus 2 plus 2 times del of n plus 1 plus 0 times del of n. Here if you can see, it is simply 0. Here the amplitude is 2 and the position is -1. So we have advanced impulse. And next comes the delayed impulses, where the amplitude of the impulse at position 1 is 1.5 minus 1.5, and that of impulse at position 2 is 1 multiplied by del of n minus 2. So the criteria that we had chosen earlier, where a given signal, elementary signal, if it can be decomposed into impulses, then y of t can be known. That is the claim we have set. And let us see, according to our claim, what should be the characteristics of a given system. Okay, let us see the characteristics of a given system first, and then let us try to understand how this works. So as I am claiming input is del of n, my output will be h of n, right, for any given system S. Now, if I say my system is linear and time invariant in nature, if I append the clause of linearity and time invariance to my system S, what happens is, as you can see clearly, if I multiply impulse by n by 1, the output will also be multiplied by 1 basing on the concept of homogeneity. Likewise, if I have del of n plus 2 plus 2 del of n plus 1, based on the concept of time variance and time invariance, as well as additivity, as well as homogeneity. We are trying to integrate all the three here. So what happens here is 1 multiplied by del of n plus 2. So the output will be again 1 multiplied by h of n plus 2, because I've already claimed that my system is linear and time invariant in nature, plus 2 multiplied by h of n plus 1. Likewise, if you see the right hand side of it, the left hand side of it, the left hand side is basically, if you assume if this is input to any given LTI system, the right hand side would obviously be its corresponding output, So now going back to our representation of impulse, if this is my input signal, then my output signal can be clearly written in the form of impulse responses, right? In the form of impulse responses. So we go forward with this concept and we assure that until and unless the system is LTI in nature, we cannot represent the input in the form of impulse responses for different times and for different weights. Okay, that is what is important, right? Going forward now, let us generalize it, and let us understand the concept of LTI system and why it is important for any system to be LTI in nature, for us to bring in a new concept called as convolution into picture. Okay, so now let me assume that if a del of n is given as input to a system S, then h of n is the output. We are doing the same thing again and again. If I assume that the system is time invariant, then del of n minus n naught will give the output h of n minus n naught, right? I hope all of you understand that. Now if you add the concept of homogeneity, I'm splitting linearity and I'm multiplying my impulse with x of n naught, and I hope all of you understand that x of n naught is a constant. It is the value of x of n at that particular time n naught, right? X of n naught is a constant, because homogeneity here on the right hand side also we have it multiplied by constant, extending this concept to additivity. Then I can write summation n runs from minus infinity to infinity x of n naught del of n minus n naught will give the output summation n runs from minus infinity to infinity x of n naught h of n minus n naught. This is n naught because not n, it is n naught, every value of n. So if I assume this to be my input to the system, my input to any given LTI system, then the output of that LTI system is on the right hand side. So how do we write y of n? Y of n is equal to summation n naught runs from minus infinity to infinity x of n naught h of n minus n naught. This is nothing but the convolution of x of n with h of n. We have seen what convolution is in unit 2, and we end this lecture by concluding that if a system is LTI in nature, then its output y of n is a convolution of its input with the impulse response. Now let us see the simple representation quickly. X of n, now it changes completely. Y of n, the regulating body is h of n. The system is LTI in nature. We'll continue in the next lecture. Thank you.